لاب 6 نقصت فيه تقريبا، جبت 8.
هو أنا بدأت أصحح من لاب 6. اللابات اللي قبل لسه ما صح. ف يعني حتشوف الدرجات كيف حتطلع معاك لاب. ف خلي الدرجات كلها تطلع وتصير انت. بحاول أخلصها في أقرب فرصة، وتشوفوها إن شاء الله الدرجات. وغالبا يعني كتبت لكل شخص في الكومنت إيش الجزئية اللي كانت عنده الإشكالية فيه.
والله دكتور نحن نحاول نسوي الأفضل يعني، ولا مع الواحد إلا لاب برفورمانس منه.
إيه، أعطوني لحظات بس أشيل الأخبار. طيب، بالنسبة لللاب performance، إذا في أحد أحب إنه يعرف تفاصيل أكثر، أمور أكثر، ممكن نتكلم خارج الكلاس عشان يكون في وقت نخلص الماتيريال المطلوبة مننا اليوم. ولو تسمحوا لنا بس في النقطة.
أوكي.
الله يكرم. طيب، اليوم مثل ما ذكرت لكم بالنسبة للماتيريالز، فتلاقونا حننتقل من presentation إلى text book إلى أجزاء أخرى في البرزنتيشن من مناطق مختلفة. فودي إنكم بس يعني طولوا بالكم معانا عشان نقدر نشوف كل المطلوب هذا الجزئية من الكورس. طيب، نحن أول شيء خلينا نسوي شير سكرين عشان تشوفوا معايا. أنا بحاول أسجل المحاضرة هذه وارفعها لكم. انتوا جاكم الرابط في لقاء من اللقاءات ما استطعنا ان نسجله داخل البلاك بورد، ورفعته لكم وارسلت لكم الرابط، صحيح؟
ايه صحيح.
اي ممتاز. ان شاء الله بنحاول
إيه.
بقدر المستطاع نسوي نفس طيب، مثل ما انتم شايفين الان نحن تكلمنا عن اللابلاس ترانسفورم، قارناه مع الفورير ترانسفورم والديفاين Laplace transform. Then we go to the region of convergence, and after that we have covered the properties of Laplace transform. الآن we will cover more properties of Laplace transform, and we will get more examples to make it much clearer. I think we've covered up to this point here. And region of convergence, yes, all of them we have covered those points. طيب، كل هذه غطيناها. Now I just want to put more emphasis on this table. Now, from beginning till here, we're talking about bilateral definition of Laplace transform. There are two definitions of Laplace transform. The first one is bilateral. So this table is based on bilateral definition of Laplace transform. The unilateral we will have it as the section at the end of the chapter. We will see also the definition of Laplace transform as a unilateral, and there is a different symbols that refers to the unilateral Laplace transform. So I just want to make sure that this is bilateral. So whenever we have this shape of Laplace transform and this table and all these properties are linked to the bilateral. And as an agreement that if you're moving from time domain to S domain, we're having this symbol, the capital L, which is a bilateral Laplace transform, which moves from time domain to S domain. So this is شوف الآن شغال معايا هذا اللوح بدون أي مشاكل. ما أدري إيش مشكلته، بعض الأحيان يسوي لي مشاكل غير طبيعية. إن شاء الله إنه يكمل اللقاء وهو طيب يعني. طبعا this symbol is bilateral Laplace transform. The unilateral is not only this letter. The unilateral it will be U and then طلعت المشاكل then the L later. So this is unilateral definition of Laplace transform. And this is not included on this table. It has some different table, and you have to take care about this. So just I want to make sure that this point is clear to you. طيب. Now let's see the properties, and we have covered this. We know how to move from Laplace transform to Fourier transform, and back from Fourier transform to Laplace transform. And we have seen what is one of the benefits of using Laplace transform is to generalize the idea of Fourier transform not only on frequency response, but for the system response and the entire system transfer function, to understand the system, whether it is stable or unstable, and how can we work with unstable system to bring them back into stability. About these two properties we have covered it last time, and we have identified that in Fourier transform we are trying to name it as frequency response after the transformation, but here the function is called the system function after the transformation in Laplace transform. We have covered the stability, causality, and identify. Whenever we look at the Laplace transform, we could tell whether it is stable or not, and the condition is if inside the region of convergence we do have the j omega axis, or we could say the imaginary axis, then it is a stable system. And for causality, we should know, or we should notice that the region of convergence to the right of the rightmost pole. And if we do have, if we do want to combine both conditions, causality and stability, then all poles should be to the should exist only on the left half of the SP. Type. We have seen this first order system, and we know that, or we came to know that the first order system, or the differential equations, will give us part of the information. So by this differential equation, we will not be able to identify the complete idea about the system, but we need some auxiliary information, like if it is a causal, or if it is not causal, or if it is stable or not stable. And based on this auxiliary information, we will be able to identify the complete solution. So whether it is this solution or that solution. Now let's take another example starting this class. So this is a second order system where this is the differential equations. So why did we say this is a second order? Because we have the second derivative of one of these variables. So whether the input or the output, we do have a second derivative, then we call it a second order system. So if we took the Laplace transform of the entire equation, then for the first term we will have s squared. For the second term we will have 2 times s. This is the constant. So it will be 2 times this constant, and the s came from this term because it is the derivative of y. Then the last one, there is no s, so it will be just this constant. So we got these terms from the first, from the left hand side, and then as you know there is a common factor which is capital Y of s, as you can see. So we can do it on 2 steps, or we can do it only on 1. Then from the right hand side there is no different derivative taken to x, so there is no x, there is no s. Then we just simply put this constant here and multiply it by capital X of x. طبعا as some of you asked me in before the lab exam, if we do have this is the Laplace transform, and this is exactly similar to how we deal with discrete time Fourier transform, or with the Fourier transform too. If we have such a differential equations, then what we're looking for is capital Y over capital X. So if we did the math here, a property, then the factor that is multiplied by Y would come on the denominator, and the factor which is multiplied by x, it will come on numerator. So this is n of s, and this is e of s. And some of you has switched between these two polynomials, which is wrong, and you have to know why this is have been done in this. Anyway, now after we have got to this form, then we could factorize the denominator, which is d of s, to be equal to these two product of these two factors. And if we did so, we need to define the constant c1 and c2. And if we use the mathematical operations, very famous formulas, so we could come to know that this is C1 and this is C2. Just I want to highlight that this is a zeta. This zeta is exactly the same as this zeta. So this is called zeta, which is somehow this form. Right. So from here we can see that this part and this part is exactly the same. And what is the difference is here. This is plus and this is minus. So these two poles are conjugates of each other. Please. Right. So the main difference between these two, C1 and C2, is they are conjugate. So in other words, C1 is the conjugate of C2. Okay. Now, what we need to understand here is to try to see how these poles are changing based on this value of zeta or of omega n. Now let's see how these things are changing. Now, if zeta was less than 1, then if we put the zeta less than 1, then a number which is less than 1 minus 1, we will get complex number. So we will get square root of minus 1, which is somehow a complex number. So if zeta were greater than 1, then it is a real number. There is no problem. There will be a real number. Now let's see how these things are changing. Again, this is the zeta, which is changes, and when the zeta is changing, we have to fix omega n to observe how these things are affecting our results. So if zeta was equal to 0, then the poles will be on j omega axis. So if zeta was equal to 0, so this is equal to 0, then this will go to 0, this will go to 0, and this will be square root of minus 1, which is I. So it will be plus omega n I and minus omega n I. And as you can see that it will be plus omega here n and minus omega n, and this is on the j omega axis. If the and we know that to have a stable system, we have to have all these poles on the left hand side. So in this case, they are not on the left hand side. They are marginally, what we call it, marginally stable. So they are not stable, but they are marginally stable. Now, if we do have zeta greater than 1, so these are the two ends. If it is equal to 0, then it is marginally stable. If it is greater than 1, then the poles will be on the real axis. As you can see that the poles will come into this axis and it will be on real axis, and there will be no complex numbers. Now, if we do have the zeta in between 0 and 1, then it will be on the left hand side and it will be in this area, as you can see.
Doctor,
Now,
what is the differences between first order and second order in Laplace here?
for the first order, as you can see, there is only one pole, S plus A, and the pole is S equal minus A.
Yeah.
And based on these first order and second order, we will be able to work with the systems in appropriate way to do the required changes in the system to make the system stable. So if we are able to understand how these poles are moving and we want to push these poles toward left hand side, then understanding these factors, طبعا first order is very clear. Just push the pole to the left, that's it. Like in the right hand side, you have to factorize this second order system into two factors, and then look at this zeta to make sure that you choose a correct value of zeta to put the poles on the left hand side. فكل الكلام اللي نحن قاعدين نحاول نقوله هنا هذا حيفيدك في السيستمز لما تنتقل على السيستمز الكورس حق السيستمز والكنترول. You will be able to understand how to make the system stable and what are the factors that you need to take care about it so you bring the system into stable region.
Doctor, sorry, but in physical systems, does zeta represent something?
Of course, لما أنت you do derive these equations, these will be like physical values. like مثلا بعض الأحيان يقول الgain حق مثلا one of the op amp, it will be the omega, and the other gain will be the zeta factor. فلما أنت تعدل في الجينز هذه وتغير فيها هتغير السيستم ترانسفير فانكشن، وحتشوف إنه في حالات معينة هتصير ستيبل وفي حالات معينة تصير unstable.
اوكي.
ففي النهاية أنت لما تسوي الديريفيتيف درايفنج للترانسفير فانكشن هذه you will link these numbers that we're talking about to the parameters in your systems. Maybe this zeta has a certain equation which has maybe more than one factor to bring it into this zeta. يعني لما تكون في physical case مثلا transfer function هذه representing something in front of you, you will find out there is a relation between السيستم اللي قدامك الفيزيكال سيستم وهذا الايكويشن، ولو حطيتها بالصيغه هذه رتبت الايكويشنز بالصيغه اللي نحن قدامنا حتحصل انه الزيتا is defined by some factors or some properties of this physical system.
Okay.
طيب, now if we're talking about the frequency response, we just simply look at the j omega axis and look at them to understand the frequency response and the Fourier transform. And to do so, we will just simply put S equal j omega. فإذا نحن نبغى نشوف كيف السيستم بالفريكونسي domain how they behave, نحن we just simply put S is equal j omega. هذا نحن اتفقنا عليه من البداية إنه إذا نحن نبغى ننتقل من Laplace Transform to Fourier Transform, we just simply put S is equal to j omega. In other words, we're letting sigma equal to 0. طيب, if we evaluate the transfer function, then we will be able to predict the frequency response. طيب, طبعا we do have here two S's. So if we put these two S's by equal to j omega, we will see how we could analyze the Fourier transform or the frequency response of the system. Now I will show you an example. يعني انت ما حتقدر تحطها بيدك وتقدر تحسبها واحد واحد، لازم تحتاج كمبيوتر عشان تشوفها. بس انا بوريك كيف لما نرسم الفريكونسي ريسبونس او لما تطلب من الكمبيوتر يرسم لك الفريكونسي ريسبونس ليه قاعد يطلع بهذه الصورة وبهذه الطريقة. خلينا نشوف مع بعض. يعني قبل ما نوصل للرسمة خلينا بس نشوف كيف الفريكونسي ريسبونس هذا ليه يطلع بالشكل اللي نحن شفناه. طبعا let's consider now this example. We have two poles. This is the first pole here and there is the second pole. طيب طيب الآن these are the two poles. يعني أنت حليت السيستم وطلع في النهاية you do have these two poles. الآن تبغى تسوي plot للفورير transform magnitude. Now what we need to evaluate, set s equal j omega and evaluate h of s, and this will give you what? The frequency response. Right. Now if we look here, when you set s is equal j omega, omega will change from 0 all the way to infinity. Now when we change omega from 0 to infinity, you will notice that you are moving along this axis. شايفين انتوا البوينتر ولا ما انتوا شايفينه يا شباب؟ You will be moving along this axis. لكن انا ابغاك تتخيل معي انه الان حنرسمها بشكل عكسي، فحيكون الفيرتيكال اكسس هو horizontal اكسس. شوفها انت بعد شوي. فهذا الاكسس we will flip it and we will draw it this way. It will be horizontal. And we will start changing the omega, and we will see how this h of s, magnitude of h of s, is changing. طيب these are the steps. So the geometry الآن أنت ممكن تحلها mathematically، ممكن تحلها geometry. فأبغاك أنت تتخيل معي geometry بالحساب الرياضي والشكل الهندسي والأبعاد، هتفهم ليه يطلع الفريكونسي ريسبونس بهذا الشكل. فنحن we having a complex numbers minus a complex numbers. So what is this? This is a complex numbers minus a complex numbers, and this is we got it from here. You see? الآن أخذنا واحد من هذا الفاكتور حطيناه هنا، هو عبارة عن complex numbers minus a complex number. طيب when we have a complex number, we can represent each complex number by one vector. So this is C1. If this is the pole, then this is C1, which is this guy. And the point that we have chosen omega to be is represented by this vector. Now, if we subtract this vector minus this vector, we will have this vector, which is, in other words, it is a distance between this point and the point that we are moving along this axis. هل هذه النقطة واضحة يا شباب؟
Sorry, Dr. again.
طيب. الآن this h of s, we're trying to take the absolute value when s is equal j omega. طبعا نشيل ال s ونحط بدالها j omega وناخذ ال absolute value. لما ناخذ ال absolute value عبارة عن omega n square constant، رقم ثابت، divided by هذه two product of two numbers. طب what are these two numbers؟ ناخذ واحد ناخذ الأول نحطه هنا، عبارة عن j omega minus c. ال j omega عبارة عن complex numbers اللي هو عبارة عن الفيكتور هذا، because we're moving along this axis. ال c عبارة عن الكونستانت، عبارة عن البول اللي نحن معرفينه. فلما نطرح complex number minus a complex number, it is nothing but just the distance between them. وضحت؟
Okay.
طيب الآن هذه هي النقطة الأولى اللي قاعدين نتكلم عنها هنا. فواحد من هذه قاعد يحسب لك الديستنس بين النقطة هذه وبين المكان اللي نحن قاعدين نمشي عليه. الثاني حيحسب لك الديستنس بين النقطة الثانية والمكان اللي نحن نمشي عليه. واضح؟
Yeah.
فحنضرب المسافة هذه، قول هذه المسافة مثلا 3، وهذه المسافة 4 حنضرب 3 ضرب 4. لا أبغاك تتخيل معايا this is the product of length of vectors observing length of vector. هذا الكلام المكتوب هنا. فالآن أبغاك تتخيل معايا إنه نحن when we are moving along this axis we're trying to take the product of this length times this length and omega n divided by this product. فحط هذا في بالك ونحن نرسم الرسمة حتشوف كيف نفسر هذا الكلام المنطقي. Note as we get closer to the pole we get shorter, hence frequency response would start to be. لما نقترب من النقطة هنا أقرب نقطة في الأكسس هذا إلى البول هذه هي عبارة عن هذه النقطة، صح ولا لا؟ فلما نقترب من هذه النقطة حيكون هنا أقصر مسافة، فلما تكون هنا أقصر مسافة هنا أقل رقم فالفاليو هنا حيكون أكبر ما يكون. خلينا نشوفها الآن على أرض الواقع. طيب هذه البولز في البداية وهنا بداية السيميوليشن اللي نسويه ونبغى ناخذ the distance between these points to the poles to the omega that we are starting with. طيب هنا حط في بالك just that the magnitude of h of s is the reciprocal of the product of the vector's length. فهذا الطول ضرب هذا الطول واحد عليهم عبارة عن يعني ال h magnitude of h. فالآن نبدأ من الصفر، عبارة عن رقم constant مضروب على هذه length في يعني تطلع لك قيمة معينة ورسمناها. لما تبدأ تقترب when we are approaching the first pole this value will start to go up and once we reach to this point we will see that this is peaking up to the peak. This is the maximum. The maximum reach when this is just parallel or very close to the first pole. And when we go further, moving further, it will start decaying again. And once we reach infinity, this will go to zero because this length will go to infinity. So this will go to zero. But this is what we are trying to analyze. Why the frequency response of the system looks like this. Now we get a deeper sight of why do we have this frequency response to our system, because the poles are located in this location. Is this clear يا شباب؟ هذا جزء من مفهوم الترانسفير فانكشن واللابلاس ترانسفورم اللينك between them.
Yes, doctor. But what about the other pole below it?
هنشوف الآن لو إننا حركنا في النيجاتيف سايد هنرسم البلوت من الجهة الثانية فحتلاقي زي ما صار هنا في بيك حيجي هنا في النيجاتيف سايد حيصير بيك ثاني إلى ماينس انفينيتي حيصير إلى الصفر مرة. فنفس الرسمة هذه حتصير duplicated زي الإيفن فانكشن في الجهة الثانية. طبعا نحن بعد ما نمشي في السلايدز حتشوف الرسمة هذه بالتالي. بس الآن هذه الجهة واضحة. أوكي؟
Yes.
طيب let's move. Now what about if we start moving these poles? الآن نحن فهمنا السيستم. We understand the system. Now I want to move البولز عشان أحرك من unstable system to stable system مثلا. بس وأنا أحرك أبغى أفهم إيش يصير معايا في الرسم. طبعا يا شباب الكلام هذا لينك بشكل كبير مع الماث، فإذا أنت يعني تحتاج أشياء إضافية أسأل عشان أحاول أشرح لك هي. أنا أتخيل إنه في أمور مفهومة، إذا في شيء مو هو مفهوم رجاء أسأل. كل الكلام اللي نحن قاعد نتكلم عنه مرتبط بشكل كبير مع الماث والgeometry of these things. طيب الآن خلينا ناخذ cases. عندنا 4 cases خلينا نحاول نفهمها. What about if we start now this poles gives this frequency response. يعني هذه الرسمة الأولى، المربع الأول اللي في اليسار عبارة عن كل هذا سويناه. طيب بدأنا من الصفر إلى انفينيتي وبناء عليها رسمنا الرسمة. فالبول في هذه المنطقة أعطتنا هذه الرسمة. الآن what would happen if we start moving these poles vertically and apart from real axis؟ قاعدين نحاول ندفها بعيد عن real axis up and down. When we move it up and down apart from the real axis, the يعني هنا the resonant frequency was here, which is related to this point. And when we move it up, this resonant frequency will move along with this poles. So this is, we're moving it down here and up, then these poles will move apart from imaginary axis. So what we're doing here, we're pushing the peak toward right side toward infinity. So the resonant peak shifts to infinity. And another point, this peak becomes a little bit weaker. And the reason why, because these poles are apart from each other. So whenever it is apart from each other, as you remember here, a length between them are multiplied by each other. لما انت تبعدهم عن بعض ففي واحد حتقترب منه لكن في نفس الوقت حتبتعد عن الثاني مرة كتير. فواحد حيزيد والثاني حيقل، فلذلك حتلاقي البيك هنا ضعف معك. طيب ايش يصير لو ان بدينا نعكس العملية ونقترب؟ we are moving towards real axis. This will move to the zero. يعني this peak will move this way, so it brought closer and closer to zero, and it becomes stronger. Why? Again, it is the same. إذا جعلنا هذه البولز قريبة من هنا, they will become both together high, short. Whenever we reach to one of them, the other one is still, it is short, it's not too far away from each other. So both are short in the same moment, so the magnitude of the entire function will be greater than if they are apart. So we notice that the peak becomes stronger and closer to the 0 point. Right. This is the first part when we move vertically apart or towards real axis. Now, let's try to move it horizontally. Move these poles horizontally towards the imaginary axis. So if we are moving it towards the imaginary axis, do you think this omega position will change? No. Because when we're moving along this axis, the shortest point will remain on the same point. There is no change because it's always here. But this will not shift anywhere. So the resonant peak does not shift anywhere. But because we are coming closer, so the distance between the poles and the j omega axis will become smaller, and therefore the magnitude, which is the reciprocal, will be greater. So the peak starts to become narrower and higher. Now, if we go to the other way, move it apart from imaginary axis, then it will, again, the resonant frequency, the resonant peak will not shift, but it will become wider and it will go lower magnitude. طيب وضحت يا شباب؟ في سؤال هنا؟ هل عندكم أي سؤال؟
Doctor, if you want to know as a practical example for this, what frequency response mean in practice?
ممكن كلها هذه، أي واحد من هذه ممكن. يعني بعض الأحيان أنت تبغى you want to come to this shape, or maybe you want to go to this shape or to that shape. Maybe you want to change your resonant frequency. Now, if you want to change the resonant frequency, should you choose to move horizontally? No. If I want to move change the resonant frequency, I have to move vertically. If I want to increase my magnitude or narrow my frequency response without changing the resonance frequency, then I will choose this. Is that clear?
Yeah.
Right. Now before taking the break, I will show you this. So this is what I was talking to you before. This is the complete picture of positive and negative sides of omega. So this is the right side and this is the left side. And as you can see that taking certain values of zetas will change the peaks. Since omega n is exactly the same, we did not change the omega n, we just changed the zeta, then these values will start peaking on the same resonant frequency. So when we pick a smaller zeta in frequency domain corresponds to the poles moving closer to j omega axis and correspond to frequency response getting peaker. Now in the time domain, this is the frequency domain. What happened in the time domain? We know that C is the solutions for us here. As you remember, the C1 and C2 will be the exponent in the exponential functions. Then given that property, when we bring zeta smaller in time domain, the oscillations is the same. So the frequency will not change. It will oscillate on the same frequency, but the exponential damping become lesser. So in the first time it damped quickly. In second damp, it is damped much slower, and at the end it is almost damping very, very slowly. طيب. I think we should stop here for a break. ناخذ 5 دقائق يا شباب ونرجع بعدها نكمل الكلاس إن شاء الله. فكرة أنا ما قلت إن شاء الله، فجاني اتصال من مدير القسم، رئيس القسم، وتأخرت عليكم. طيب يا شباب، فين وصلنا نحن؟ في أحد عنده سؤال؟ إلى هذه النقطة في أحد عنده سؤال على شيء من الموجود هنا تكلمنا عنه؟ رجاء إذا لا عنده سؤال يسأل يا شباب. طيب نكمل. طبعا كثير من many of the higher order systems in real life, it's not only first and second order, it's higher order systems. Many of these higher order systems.
Sorry, the slides you're not sharing.
تفضل.
You didn't share the slides.
Oh, okay.
Okay.
Thank you. طيب. So we're talking about yeah. Again, so this is, if you do have any questions, please let me know if you have any questions. Now, for higher order systems, in our real life, it is not only first and second order systems, but there are many higher order systems. For higher order systems, we can combine to implement higher order systems, combine first order and second order systems. And there is, as we've seen before, there are many ways how we combine systems. If we go with cascading them this way, so one after another, then what would be the transfer function? The total transfer function would be the product of all these transfer functions. So if this was second order, this is second order till you get to the end, then the total transfer function of the entire system, the system function, will be of 2 times n. So if we have 3 systems cascaded, then we will have the order of the complete system will be 6. So 3 systems we have to multiply by 2, it will be 6. The order of the system is 6, and so on. So we could get the higher order with cascading it down as you can see here. So a second alternative is to go with parallel, and if we go with parallel, then these will be added together. And as you know, when you add some rational functions, so n1 over d1, n2 over d2, n3 over d3, and so on. So you have to unify, or you have to get a common denominator, and then to find the common denominator, the order of the system will increase. So to get a common factor here, again, the denominator order will be 2 times. So if this is a second order system, and this is second order system, and this is second order, again, the entire system, the denominator will be of 2 times n. If this is 3n, n equal to 3, then the denominator will be of order of 6. Let's take an example, which is what we call it speech synthesizer. أنا أرسلت لكم رابط لهذا الفيديو يا شباب. speech synthesizer.
يس دكتور.
شفتوا؟
حق MIT
ها؟
اللي هو كان حق MIT.
حق MIT صح. وين راح؟ شفتوه يا شباب؟ في أحد ما شافه؟ نحتاج نعرضه مع بعض ولا خلاص شفتوه؟
أنا والله ما شفته دكتور.
حتى أنا والله ما شفته.
طيب خلينا نفتحه مع بعض ونشوف. هل أنتم شايفين معي الشاشة؟
يس.
طبعا إيش السبيتش سينثسايزر؟ طبعا هالكلام هذا قديم، لكن يشرح لك الكونسبت اللي في المادة هنا، وكيف انك باستخدام الكونسبت هذا تقدر تطلع اشياء كثيرة، والى الان مستخدم، نفس المفهوم مستخدم في digital systems. لكن انت الان لازم تفهم how did they were able to come up with such systems, and then they have modified to reach to whatever we can see these days. الفكرة كلها انه يقلد صوت الإنسان. الحبال الصوتية داخل صوت الإنسان عبارة عن مجموعة كبيرة من الحبال تتحرك وتتذبذب بطريقة معينة، فلو إننا قدرنا نفككها إلى أبسط درجاتها ونطلع الفريكونسيز اللي نحن نبغاها ونجمعها بطريقة معينة، نستطيع نطلع صوت الإنسان بشكل أو بآخر. فهو الآن في الجهاز هذا we do have 4 second order systems in parallel. كل second order system له resonant frequency. بنفس الطريقة الحبال الصوتية داخل حنجرة الإنسان فيها resonant frequency. فلما تحاول تجمع بين هذه ممكن انك تغير الريزونانت فريكونسي هذه. كل ريزونانت فريكونسي تتغير بالناب اللي انت شايفه، هذا 1 2 3 4 نابس تغير فيها الريزونانت فريكونسي. فبنفس الطريقة داخل الحنجرة الحبال الصوتية كل واحد من الحبال الصوتية تتغير الريزونانت فريكونسي بآلية معينة في جسم الإنسان، يستطيع من خلالها يطلع الأصوات المختلفة. طبعا أنت لما تتأمل في جسم الإنسان وكيف أن الله سبحانه وتعالى أعطاك هذا كامل وأنت ما تفكر كل هذه تعمل بشكل سريع جدا. شوف هو قاعد يحاول بكل الآن حتشوف أنت يعني كل المحاولات اللي قاعد يسويها وفي النهاية يطلع صوت يعني حتى يعني بعيد، ما هو مثل صوت الإنسان، يحاول يقلد صوت الإنسان فقط. فأنت الآن بس بدك تتخيل معايا الكومبلكسيتي اللي موجود في داخل حنجرتك عشان يولد هذه الأصوات، وكلها عبارة عن سيجنالز وسيستمز. هذه كلها عبارة عن سيجنالز وسيستمز داخل حنجرة الإنسان. فالآن هو إيش بيحاول يسوي؟ يحاول يضبط الريزونانس في الأربعة، يعني زي مثلا عندك 4 حبال صوتية تضبط الريزونانس فريكونسيز في هذه ال4 وبعدين تبدأ تطلع صوتك من داخل طبعا الاكسايتيشن هذه اللي هي الاكس اوف تي اللي هو زي الهواء اللي يدخل او اللي يطلع من داخل صدرك عشان يمر من خلال الحبال الصوتية، عبارة عن impulses زي هذه الامبلس. فنحن we are putting impulses into our systems to excite it عشان تشتغل، وبعدين we are summing up the results and getting into the sound. طيب خلينا نسمع كيف قاعد يسوي الحركة.
Center frequencies, there is a control representing the center frequency of the third resonator and the fourth resonator, and those are represented by these two knobs. And then the first and second resonators are controlled by moving this joystick. The first resonator by moving the joystick along this axis, and the second resonator by moving the joystick along this axis. And then in addition to controls on the 4 resonators, we can control the fundamental frequency of the excitation, and we do that with this knob. So let's first of all just listen to one of the resonators, and the resonator that I'll play is the 4th resonator, and what you'll hear first is the output as I vary the center frequency of that resonator. So I'm lowering the center frequency, and then bringing the center frequency back up. And then, as I indicated, I can also control the fundamental frequency of the excitation by turning this knob, lowering the fundamental frequency, and then increasing the fundamental frequency.
سمعين الأصوات أنتم يا شباب ها؟
Yes.
Switch in the other resonators. When we do that then, depending on what choice we have for the individual resonant frequencies, we should be able to synthesize vowel sounds. So here, for example, is the vowel E. Here's and of course we can generate lots of other vowels.
فالآن هو قاعد يطلع لك فقط أصوات حروف العلة. بهذه الآلية يجمع هذه كل الفريكونسيز وفي أماكن محددة بريزونيترز معينة. الفريكونسيز ضبطها بطريقة معينة حتى يجيب لك الفاول ساوندز، وزي ما تسامع الساوندز هذه يعني مش 100% صوت الإنسان، لكن بيحاول يقرب لك الصورة. طيب خلينا نكمل معه.
Vowel sounds and change the fundamental frequency at the same time.
في النهاية أعطاك مثال إنه بيحاول يقلد how are you مثلا، كيف تطلع بالحركات السريعة اللي يقدر. فهذا what we call it analog speech synthesizer. طبعا في بعده طلع أشياء كثير اللي هي digital speech synthesizer، ويكون عندك يعني زي الكيبورد تكتب فيه الحروف ويطلع لك الأصوات. والآن حتى في الكمبيوتر ممكن تكتب أنت الكلام وتخلي الكمبيوتر هو اللي يقرأ لك هو بطريقة أو بأخرى. طبعا كيف هذا يصير وكيف الفيزيكس اللي behind it كلها حتستطيع تفهم وتتعامل معها لما تستطيع تتحكم بالأصوات وتتحكم بالfrequencies وتحاول combine them together as you can see here. طبعا this is four resonators, each one has a second order systems. Then we could achieve this. Sometimes it is 5 systems, not only 4 systems, to get to such output. طيب طب نحن كده انتهينا من البرزنتيشن هذه. خلينا ننتقل إلى الكتاب. الكتاب عندنا جزئية أحتاج إني أشرحها لكم من الكتاب مباشرة، لأنها أسهل بكثير من لو إني حاولت أقول لكم هي على طبعا what I want to explain to you here in this textbook is the properties of Laplace transform and give some examples as shown here in the textbook. So let us go to 9.5. These are the properties of the transfer function. ففي أحد عنده سؤال على اللي تونا عرضناه؟ في أحد عنده أي كومنت، تعليق، شيء؟ طيب خلينا ناخذ التحضير. أتأكد أنكم معايا، لأنه أنا أسأل الظاهر أنه ما في أحد حالي قاعد يتكلم. طيب محمد الزباني موجود؟
يس.
ما شاء الله التحضير على طول موجود.
نعم موجود من أول يا دكتور معك.
أنا أسأل أقول فاهمين، في عندكم تعليق أموركم؟ طب قولوا نعم لا، يعني ادوني أي كلمة بس.
إن شاء الله تبشير بعدين.
الله يبشر.
لو عشان ممكن في سؤال
تكون تسأل يا دكتور إن عندكم سؤال ولا شيء، فخلاص ما حد يقول.
طيب ما في مشكلة.
ساكتين هنا.
نسمع أصواتك.
أوكي.
بس. تركي الشريف.
تمام.
يس.
تركي عبد الله الرشيدي.
يس.
محمد الجهني. غير موجود. أديب الرفاعي.
يس.
عبد الرحمن الغامدي. غير موجود. عبد الرحمن. يوسف الشهابي.
يس دكتور.
محمد الجحيف.
يس دكتور.
إبراهيم الجحيف.
يس.
أحمد باقاسي. وطاهر الأغا.
يس.
طيب عندنا بس محمد الجهني وعبد الرحمن الغامدي اللي ما هو موجود. طيب نقول بسم الله. خلينا نخلص إن شاء الله properties for transfer. طبعا linearity, we have discussed this linearity before, so I will skip the linearity. As you can see, the same example was given here. So this example, if you do have two signals and subtracted from each other, then we have seen before that the region of convergence. So this is the first solution, and this is x1 and this is x2, and then if we add them together, we will get to a certain point where we get this 1 over s plus 2. So I just want to make sure that you notice that the region of convergence here is -1, greater than -1. So this region. For the second one, the region of convergence is, this is the first pole and this is the second pole. If you put them together, you have to have it to the right of them. So this is the region of convergence. Now, this region of convergence and this region of convergence is the region of convergence of both of them. Now, what happens if we combine them together? The first one minus the second one, this is the system that we do have it. So if we do the math, then this will come to this point, 1 over s plus 2. But this, which is the result, if we want to represent the region of convergence, then it will be -2 to the right of -2. So we've started with region of convergence, which is to the right of -1, and then we get the solution to a larger region of convergence, which is started at -2. I want you to go through this example and read it carefully, because there are some cases where we started with a smaller region of convergence than what we got in the end, and this is not common. This is rarely happening, but this is one of these examples. Like for the time shifting, if we're talking about time shifting, we have to go from time domain to S domain, and the region of convergence is equal to R. And if we did a time shifting here, we will multiply by exponential factor, as you can see here. But the region of convergence remains the same, unchanged. So this is very important whenever we're talking about the properties of Laplace transform. We have to consider what is the changes happening in region of convergence. So for time shifting, there will be no change on the region of convergence. Now, what about shifting in S domain? If we did the shifting in the S domain, then moving from x of s to x of s minus s0, then we will multiply by this exponential factor in the time domain. And now you have to consider a change on the region of convergence, as you can see here, r plus real part of s naught. Now, what about if we're doing a time scaling? So if this is the region of convergence, this is R1, this is the R, the region of convergence, and we want to do a time scaling, then what would happen? We will add this time scaling factor, and similar to the Fourier transform, we will have the expressions here. But the region of convergence changed from R to R1, and the factor is times A. So what you can see here is that if this is R1, if this is R, the original R, this will change to R1, and there will be some additional values to these limits R2 and R1.
Doctor, I think, I'm not sure, but I think you missed the frequency shifting above.
This one?
Below it, exactly below. The equation 9.89.
This one?
Yes. Is this for the frequency or what?
This is special case when S naught is equal j omega. So this is the Laplace transform. But if you want to focus on one special case where the S naught that we're shifting towards is having no real part, it's just imaginary part. Okay, so in this special case there is this condition where the ROC would not change.
Okay.
Only in that case. Otherwise it will be exactly the same. So S naught to be S naught the same, and S naught here is exactly S naught here, because we have set the S naught is equal j omega. But a change in region of convergence, because we are adding
Real part.
a real part in this.
Yeah.
ومشكور يوسف انك ذكرتنا نذكر النقطة.
Thank you.
طيب. Now we're moving to the time scaling. So again, so this is when we have the time scaling, we are multiplying by a factor a, and then we are dividing s by a. And since we are dividing s by a, then the real part of s, which is changing the limits of the region of convergence. So the R1 plus the real part of S1 is 0, and R2 and R1 is the same. So we have to do this shifting, moving it either to the right or to the left based on the value of S naught and the real part of this S naught. Now, sorry. This figure goes for shifting in S domain. So it was my mistake. So this is what we are adding to the real to the region of convergence, the real part of S naught. So we're shifting this region of convergence to the right or to the left based on the real part of S naught. But for the time scaling, the figure is shown here. So this is the S plane of the original signal, and after we did the time scaling, then it will shrink or expand based on the value of a, because we are dividing the limits of the region of convergence by the factor a. So we're not doing shifting here, we're doing just scaling. So when we do a scaling for the time domain, the Laplace transform expression would change, and also the region of convergence will be affected by the same factor. Right. Now I will skip the conjugate, you can go through it. The convolution, we have covered it before, and just to indicate that the region of convergence containing the intersections between the regions of each one of them. So if we're convolving x1 with x2, and we know that the region of convergence of x1 is R1 and the region of convergence of x2 is R2, so the convolution between the two signals in time domain converge gives the multiplication of them at the S domain, and the region of convergence of the total result will be the intersections between the two regions.
Doctor, can you clear the intersection mean in the graph or something?
Okay, so the intersections أنا هذا الكتاب ما حقدر أكتب براحتي لكن نكتب لكم شيء بسيط هنا. Right. So if we do have this is the S-plane, so this is real and this is imaginary. So let's say this was R1, okay, and this is capital R1, and we do have another S-plane here. I will separate them so you will not get confused. So this is real part and this is imaginary part, and this is our R2, okay, so this is R2. So what is the intersection between this and this? It would be this region between R1 and R2.
Doctor, why the region of R2 is to the left side?
الآن نحن we're not talking about whether it is stable or it is causal or whatever. Systems can have any different means or regions of convergence. هذا اللي نحن بدينا فيه. فنحن I'm just putting any example. I can have it to the right or I can have it to the left. There is no restrictions.
Okay.
But when we take the intersections between these two regions, then it will be between R1 and R2, R small 1 and R small 2. So the region of convergence, it will be between R2 and R1. So this is the region of convergence. So this is the intersection between both of them. يعني المنطقة الاثنين, both of them are converging.
Yeah.
طيب نحتاج أمسح. طيب. Do you have any other question?
No.
ننتقل. طيب. This is the convolution properties. Now, differentiation in time domain, we know that the region of convergence will continue the same. So there will be no problem with the region of convergence. It will be exactly the same. Now, if we are taking the derivative, then we will multiply by s. What about if we are taking the derivative in S domain? We take the if we differentiate in the S domain, then we will multiply by t, and we have a minus sign here. So because of duality property, then when we differentiate in time, we will multiply by s in S domain. And if we differentiate on S domain, then we will multiply by t at the time domain. Just keep in mind that we do have this minus sign on that. But I advise you to go through these examples. أنا ما أتوقع في وقت كافي إنه نمر على كل examples، لكن أنا فقط أبغى أمر على البروبرتيز كاملة وأتأكد أنكم تمروا على الإكزامز ممكن بعد. طيب, what about the integration? So when we do a derivative or differentiation in time domain, we multiply by s. So intuitively, if we take the integration, we will divide by S. And again, the region of convergence containing R intersect with the real part of S greater than 0. طيب, I would leave this initial value for final value. Now, this is the table of properties that is available for us here. And this is, again, this is based on bilateral definition of Laplace transform. So the linearity, the signal here in time domain and in S domain, and then the region of convergence where we have to have the intersections between the two signals. And when we talk about time shifting, the same region of convergence, the S domain shifting, then it will be again the same region of convergence, unless if we do have this, then we will minus the real part of S naught. And the time scaling, then we will modify the S-plane. And if we talk about the convolution, it will be the intersections, and differentiation will have at least R. Then the differentiation in S domain, we will not change any factor in the region of convergence. And at the end, the integration, we will have the intersection between the region of convergence plus this real part of S is greater than 1. طيب. This table we have seen it before, so I just will skip it. And at the end, I want to move the last part. All of these subjects we have covered in the lecture, in the presentation. I will move to the last section. Okay, so here is the what we call it the system function algebra and block diagram representation. As you know, the interconnection between LTI systems would go either in parallel or in series. So if we do have in parallel, then we will just sum them up. And if we want to have them in series, then we will take the convolution in time domain and the multiplication on frequency domain or in the S domain. So in parallel, we are adding them in S domain. In cascade or in series, we will have a multiplication on us in S domain. Now, if we're talking about the feedback system, then the result transfer function would be equal to the following. So H1 over 1 plus H1 times H2. So this is the formula. You can memorize it. If you don't want to memorize it, you can derive it through this few steps. Now, what we need to do is to have like sometimes they will give you the block diagram and they will ask you to find out what is the transfer function of the entire block diagram. So if they are based on the configuration or the connection between these two systems, then we will decide which equation should we go. Should we go with the addition? Should we go with multiplication? Should we go with the feedback formula? So for this example here, if you have to go with feedback, then you will take the transfer function of the first one and you put it there, then plus the over 1 plus transfer function of the first one times the second one. So if you do this, now just I want to make sure that this minus sign goes from -3 to here, so it will be in here, it will be minus sign. Then if you did that part, then it will be 1 over s plus 1 over 3 times 1 over s, and you will get it this way. Then if you multiply the numerator and denominator by s, then 1 over s will change to 1, and this one will change to s, and 3 over s will change to 3. So this is the transfer function of the complete figure as shown here. So there are some more examples where you can go through and see you have to make it smaller and smaller systems to be able to connect them together and solve them into smaller steps. So I just want you to go through this also section at your time before as a part of this material. Now this is the end of this chapter, and before ending this chapter, I just want to emphasize on unilateral Laplace transform concept. And if you look here, the unilateral Laplace transform does not go from -infinity to +infinity. It will go from 0 to infinity, and I just want to make sure that it is 0 minus. So it's not 0 plus, so it will start from the negative part of 0 all the way to infinity. And this is what we call it unilateral Fourier Laplace transform. So in the time domain, if we take UL, this is meaning unilateral Laplace transform, we will get this capital X, which is a little bit different shape of the previous one, and this is called unilateral Laplace transform of x of t. I don't want you to focus a little bit more here, but just I want you to know that this is the definition of the unilateral Laplace transform. We're not going to go through more details about this unilateral Laplace transform and the examples here. See, also there are properties of unilateral Laplace transform, which is a little bit different than the previous part that we have discussed previously. طيب أنا كده تقريبا خلصت كل الكلام اللي كنت بقوله عن Laplace transform. Now we do have like maybe a few minutes before we close. If you do have any questions, or we can go through some of these examples here.
I think we can go for examples.
طيب. We have discussed these. We will go to the properties, and we will take some of these examples of the property. هذا الإكزامبل so we can this example differentiation in this. So let us find the Laplace transform of x of t, which is equal t times e raised to this exponential function. Now we know that the transfer function of this without the t is equal to 1 over s plus a. Now we have to relate between this function and this function, and if you try to relate them, then let's take the derivative of this guy. So what is the derivative of this? Now, sorry, is not that way. Let's do it in another. So if we have t times x of t, so we have defined the x of t as this function. So this is the x of t. So t times x of t is very similar to what we have here. So since we have t times x of t, it gives us the differentiation from the other side. So if we do have this x of t and this is capital X of s, then if we want to have the t times x of t, we just multiply by minus sign both sides, then we will take the derivative of this. So what is the derivative of 1 over s plus a? So let's do this part. So this is capital X S. Right. So this is capital X of S, which is equal. I would write it this way: S plus A raised to power minus 1. So if I want to take the derivative of this, it will be the S plus A raised to power minus 2 times the derivative of what is inside. So the derivative of what is inside is equal to 1. So what is the derivative here is equal to 1. So if we did this, so this is dx of s by ds. And if we rearrange this, it will be 1 over s plus a whole. So this is the derivative of x of t, and we have to multiply by minus sign because there is a minus sign at this side, so we have to multiply both sides by the same factor.
Doctor,
now
where did the minus go in this case?
So the derivative of this is this minus 1 will go to the front times this guy. So the derivative of this guy is equal minus 1 over s plus a squared.
Okay.
So this minus sign times this minus sign, it goes all together.
Okay.
Right. If we repeat applying this formula again, so it will be x of s will be equal to s plus a raised to power minus 2. So if we want to do this part derivative, so the derivative of x of s by ds, it will be equal الماينس 2 نحطها في البداية، بعدين نحط s plus a raised to power minus 3. But when we reorder this, we will get x of s by ds will be equal minus 2 over s plus a cube. طبعا هذه ممكن نسميها d square، ما هي d. Okay, so this is d over d. So this is the first derivative, this is second derivative. Now if we want to divide both sides by 2, then this will go, and there should be a minus sign again in the formula. So if we consider this minus sign with the formula, this will go away. So this is 1 over s plus and if you keep doing the same, then in general you will get to this formula. So t raised to power n minus 1 all over n minus 1 factorial times this. طيب في على هذا السؤال؟
لا واضح.
طيب ننتقل إلى السؤال بعده ولا نوقف يا شباب؟ خلينا ناخذ مثال واحد بعدين. طيب consider the Laplace transform. This is x of s given by this transfer by this system function. Applying the partial fraction. How to apply the partial fraction here? This is very important question. So I have to consider a over s plus 1 squared, then plus b over s plus 1 plus c over s plus 2. I have to make this equal to this, and then I will find set of 3 equations and solve for a, b, c. Once we get the a, b, c, I will find that a will be equal to, b will be equal minus 1, c will be equal to 3. Then I will substitute this here. So كل هذه سويها هو مختصرة قال مباشرة. Applying partial fraction, we will get this. Now I have to consider the first one. So I will try to implement this formula. يعني 1 over s plus a squared. If I want to go to time domain, what is a here? A is equal to 1. So this will be t times e minus, طبعا في 2 هنا قبلها, 2 times t e, a بواحد فما حنكتبها, نكتب minus t u of t. هذه the first one. For the second one here, we will use the formula at the beginning, this one. So there is no t, so it will be minus 1 times e raised to power minus a is equal to 1 again, so it will be minus e u of t. Now the third one will be plus 3 times 1 over s, so this will be equal e raised to power minus a is equal to 2, so 2t u of t. And this is the solution. And if you look here, they have taken the u of t as a common factor. So what left from the first one is 2t, the second one minus e, the third one is plus 3e. So it is the same here, 2te minus e, then 3e. And this is 1, 1 minus 2, 1, 1, 2, 1, 1, 2. And this is the solution that we get. طيب يا شباب، أنا أخذت أكثر من الوقت المطلوب. الله يعطيكم العافية، وإن شاء الله نشوفكم على خير.